All right, everyone. Today we're going to be talking about Cantor's diagonalization argument and amazing results in computer science that follow this argument. Okay, let's dive right into it. So the central question that Cantor helps us understand is if all infinite sets are the same size. More precisely, the question that we ask is, can the real numbers, even in a limited range, let's suppose from 0 to 1, be put into 1-to-1 correspondence with natural numbers? And Cantor's answer to that question is a resounding no. But before we start with that, let us talk about some sets of numbers that do not look equal or comparable, but we can still draw some interesting results about them. For example, one of the first results we may be interested in looking at is that there are actually as many natural numbers as there are even natural numbers. Now, this purely looks counterintuitive because obviously there are more natural numbers than there are even numbers. Even numbers are a subset of the natural numbers, in fact, half of them. However, we can actually show a correspondence that's a one-to-one relationship between even numbers and natural numbers. We can say that the correspondence is that for each natural number, pair it with its corresponding even number, which is 2 times that natural number. So 11 would get paired with 22, 13 would get paired with 26, etc., etc. Now we observe that every natural number has a corresponding unique even number, and unique even number has a corresponding natural number. Therefore, by observing that one-to-one correspondence, we can reach the conclusion that there are as many natural numbers as there are even numbers. That's our first interesting result. Actually, the same argument can apply to any countable set. Let's suppose we think of prime numbers. Prime numbers, they become quite rare as the numbers get larger, but still there are infinite primes, right? If you want to see that there are infinite primes, let's suppose there are finite primes, then you can multiply all of them, add 1. That would not be represented by any existing prime number within your assumption. Therefore, we know that there are infinite primes. Now let's consider the ith prime. Now we pair this ith prime with the ith natural number. Now once again, every natural number has a corresponding prime number, and every prime number has the corresponding natural number. Therefore, again, we have a one-to-one correspondence, and therefore there are as many natural numbers as there are prime numbers. And we just use this term countable set. Now, countable set is something that we can count, that we can impose an ordering on, a counting principle on. Not that these sets are finite, they're infinite, such as natural numbers. So it's not that we can finish counting, but we can at least start counting. At least we can count for the part of the set. Another question can be, what about rational numbers? Now, if we try to impose an ordering, we may have a bit of trouble. For example, if we think of 2 rational numbers, let's say 4 by 17 and 5 by 17, we can see that there are rational numbers that are between those 2 numbers, such as 9 by 34, which is basically 4.5 divided by 17. So it may appear that we cannot order them, because any 2 rational numbers that we try to order, we can put a rational number in between. However, we can actually order them, we can count them, if we don't confuse ordering with ordering by value. Now, in the previous cases, even numbers and prime numbers, ordering and ordering by value was the same thing, but in this case not. So we can in fact order the rational numbers by the following method. We think of the fraction p by q such that p and q are co-prime, so that means that the fractional number is in its simplest form. Now we allow only p to be negative, q to be negative doesn't make any sense. We can have, if only q is negative, then we can make p to be negative, and if both are negative, then that's effectively the same as both being positive. So we assume that only p is negative without any loss of generality, and we sequence them in the increasing order of S is equal to P, the absolute value of P, plus Q. And roughly, if we were to look at an ordering diagram, it would look like this. We would first start with 0. We would go to -1, 1. Then we would go to -2. We would go to -1/2, 1/2, 2/1, etc. And we would kind of keep do it that way. So that's basically how we would order the rational numbers. Once we have imposed a rational number ordering, then again we have a one-to-one correspondence with the natural numbers, and then that is true for any countable set. Again, a set is countable if its elements can be listed as a first number, second number, third number, etc. Irrespective of the value, as long as you can impose some kind of ordering, you have a countable set. That means you can count the first number, second number, third number, etc. Examples are natural numbers, integers, rational numbers, etc. Now, how would you count integers? You can count integers that start with 0, go to -1, 1, -2, 2, etc. Don't try to start from negative infinity, because then you don't know where to start from. So then the next question we want to address is, what about real numbers? Can we order them? Can we count them the same way? Now, this is where we would like to introduce George Cantor, George without the E. So a quick fun fact that George Washington University is not named after George Cantor. I only teach here, I don't name universities. So let's talk about George Cantor. George Cantor was a German mathematician, born in St. Petersburg, later worked in Halle. He was trained as an analyst. Now his job, what he was trying to do was to study trigonometric series. He was not really studying set theory. There wasn't really such a field yet. So he did not come by and say, oh, I want to compare infinite sets. Rather, he was trying to find he was trying to understand Fourier series, and his key observations was that some infinite sets seem to be more infinite than others. That's a crazy, crazy thought, right? But he persisted with that idea, and he came up with the key results. First of all, he talked about the one-to-one correspondence that establishes that sets are of equal sizes, example that we just studied, such as rational number and the natural numbers. And he also came across uncountable sets like real numbers that exist, which do not have any one-to-one correspondence with the natural numbers. Let us understand Cantor's proof here. Cantor's proof is a proof by contradiction. So we assume, for the purpose of contradiction, that all real numbers in the range 0, 1 can be listed in some ordering, such that the first real number R1 is represented by the digits D11, D12, D13. R2 is represented by D21, D22, D3, D23, etc. Again, we do not know what that ordering is. We just assume that there is such an ordering. That what we do is we construct a new number by looking at all the diagonal digits of D11, D22, D33, etc. The first place decimal point in the first number, second one in the second number, third one in the third number, etc. And we construct a new real number, x, which is equal to 0.C1, C2, C3, where C1, C2, C3 can be anything as long as it is not that particular corresponding diagonal digit. So C1 is not equal to D11, C2 is not equal to D22, etc. Now, there are 10 digits possible, so you really have a wide variety of numbers to choose from. And a simple construction that's sometimes said is that if D11 is equal to 5, then choose 6. If it's not equal to 5, then choose 5, just to make this construction a little bit more clean. But really, you can choose any number for C1 as long as it's not that exact diagonal digit here. Now, the claim that we want to make is that this new real number that we have just constructed, the real number x, is not in your ordering at all. It's not in the ordering at all because its first digit does not match the first number's first digit, does not match the second number's second digit. So irrespective of how you ordered the real numbers in your ordering principle, this number will not match that number because it will not match that digit, the corresponding digit anywhere. So this is a brand new number. Therefore, x is not on this list at all. If you say it shows up maybe much later, again remember that x has been constructed such that it does not match that number's, let's suppose that's a 1/1,000,000th number, it does not match 1/1,000,000th number's 1/1,000,000th digit. Therefore, it is not the same as the 1/1,000,000th number. So it just doesn't show up in your list at all. And that's the contradiction. So we assume that the list contained all the real numbers in 0, 1, but we constructed a real number that's not on the list. That's a contradiction. So the conclusion is very profound. Cantor's conclusion here is that the real numbers are uncountable. There are different sizes of infinity, the countable sets such as natural numbers and the uncountable sets such as the real numbers. This is Cantor's diagonalization argument, and it actually has profound implications for computer science. It is a basis for uncountability, undecidability, and it appears inside the incompleteness theorem as well as the halting problem. So it's one idea that led to many other results, many other impossibility results, and this may in fact be the biggest result in computer science that you never heard of, because even if you heard of it, you may have heard of it in mathematics. But again, a profound result by Cantor, and I hope you take something away from it.